Hey guys, how are you doing? In this session, we're gonna solve problem on diodes which are set in series. So we're gonna solve some practical problems. Just let's begin from this one. So as you see, this is the circuit. We have 0.5 volt source, and this is a silicon diode. So we have 1.2 kilo ohm resistor. So uh, as you see, to make it more clear, uh, we can draw some familiar circuit like this. As you see, the equivalent circuit can be set like this. This is the ground. So as you see, this is 0.5 volt. This is silicon. So in order for the silicon diode to begin to transmit a current through it, or to pass a current through it, it needs 0.7 volt. Its terminal voltage Vk. Vk for silicon is 0.7 volt. So uh, until 0.7 volt is delivered to this silicon diode, it would stay open circuit. So this is an open circuit. So we are asked in this example to calculate the Vd, the voltage across the diode, the Vr, the voltage of the resistor, this 1.2 kilo ohm resistor. So the voltage of this resistor, and Id, the current which flows through the diode. So since the voltage is less than the terminal voltage of the silicon, this circuit will be an open circuit, though the current id will be 0 ampere. Id will be 0 ampere. So id is the same current which passes through or which flows through the resistor. So the current which flows IR is the current which flows through the resistor is also 0. So in order to calculate VR is equal to ID times R, which is equal to IR times R. So IR is equal to 0. The VR is also 0. So in order to calculate VD is, so when this is 0, VR is equal to 0. To calculate VD, we can use KVL, Kirchhoff's voltage law. Simply, we can apply this Kirchhoff's voltage law to this circuit. So E is 0.5. We know E is 0.5. VR is equal to 0. So this, an open circuit can have different from 0 volt. So VD is equal to 0. Because, why? Because as you see, this would be the resultant circuit. This is the resultant circuit. This is the ground. So VR is equal to 0 because IR is equal to 0. There is no current flowing through this resistor. If there is no current flowing through the resistor, the voltage across the resistor will also be 0. So VR is equal to 0. E is the battery, the supply, which is equal to 0.5 volt. So we apply KVL to this circuit. So applying KVL, there is 3 components. This one, this open circuit, the silicon, so, and VR. So applying KVL, E minus this VD, the voltage across the diode is VD minus VR, which is equal to 0. We know VR is equal to 0. So we take this one to the other side. So VD is equal to E, which is equal to VD is equal to 0.5 volt. This is how we simply calculate for VD. Now let's come to the second example. So this is the second example. In the second example, this is the circuit. In this circuit, we are asked to determine the V output. The V output across this one. V output means across this one, which is parallel with this resistor, the 680 ohm resistor. So it's parallel to the 680 ohm resistor. So we are asked to calculate the V output across this. So it's parallel. The multimeter is put in across this resistor to calculate, to know or to find out the voltage across the V output. In order to calculate in order to know the amount of V output, we put the probe of the multimeter. Just practically, I'm trying to visualize. So in order to know the amount of V output, we put the multimeter across this resistor, across this, the probe of the resistor across these 2 points. So the V output is in parallel with this 680 ohm. So we have two diodes which are set in series. So as you see, 120 volt, the 12 volt is on the supply. We have 12 volt on the supply. The turn-on voltage for the silicon diode is the turn-on voltage was for silicon diode is 0.7 volt. It is given, and this is a red LED diode, light emitting diode. This is red light emitting diode. It's turn on, or VK, it's turn on voltage. So the voltage needed to make this diode transmit current through it is 1.8 volt. The turn on voltage is for this one is 1.8 volt. So this in order to calculate the V output means the voltage across this 680 ohm resistor. So to calculate this, we can apply KVL to this whole loop. So when we apply KVL to this loop, we have 4 components: the source, the 12 volt source, the 0.7 volt silicon, the 1.8 volt which is dissipated on the red LED, and the 680 ohm resistor. So these 4 components, so their combination is 0. So V output is equal to, or just when we apply KVL, we have E minus 0.7 volt, E is 12 volt, minus 1.8 volt. Just make sure to check the polarities of the diodes. When we draw the equivalent circuit, the polarity must be right. The polarity must be checked always. Otherwise, circuits which are connected with diodes are prone to so many mistakes connected with the polarity. So check polarity as much as possible. So E minus 0.7 volt minus 1.8 volt minus VR, or the V output. Or the V output is, which is equal to 680 times ID, the current which flowing through this, because the 4 components are in series. So in series, VD means ID times 680 ohm, or IR times, we can say it is IR. IR is equal to ID, because 4 components are in series. We know from fundamental of electric circuit, series components have the same current. So VD, so V output. V output, which is equal to IR times 680 ohm. So rearranging the terms, we have V output is equal to E minus VK1, VK2, VK1 is 0.7, VK2 is 1.8. So we have the V output, which is equal to 9.5 volt. So once we calculate the V output, we can simply calculate ID. We say that ID is equal to IR, which is equal to V output over R. The V output is 9.5. The amount of the resistor is 680 ohm. The resistance of the resistor is 680 ohm. So ID or IR, which is equal to 13.97 milliampere. This is how we analyze the circuit. So let's go to the third example. This is the third example. As you see, this is the third example. So we have been given this circuit. So we are asked to calculate the current which flows through this circuit, because this circuit is set in series. So 4 components set in 5 components. We have, as you see, minus 5 volt. We minus 5 volt right here, 10 volt a supply voltage. So 10 volt is supply voltage. So the current is, as you see, the direction of the current is set like this. The direction of the current is like this, as you see, I. So we are asked to calculate the V output, which is across the same to the previous example, which is across this resistor. Actually not the same, it's kind of have similarities. So in this case, we are asked to calculate the V output, which is across these 2 components. There is a 5 volt battery which is set in a 5 volt battery which have the same direction to this source, as you see, minus 5 volt. So the current enter into the negative terminal to the positive terminal. When it is said minus 5 volt means the current enter into the negative terminal, leave it through the positive terminal to the ground. That's the meaning of minus 5 volt. When we sketch the equivalent circuit, we will sketch it like this. The negative terminal, current enter into the negative terminal, leaves into the positive terminal. So we are asked to calculate the voltage across these 2 components. The voltage across these 2 components, because V output is like this. So across these 2 components, the ground is the same for these 2. So the voltage, the V output is the voltage across these 2 components. The probe is connected between this one end of the resistor and the ground. So to calculate such kind of circuit, or to analyze such kind of circuit, we apply KVL. So we apply KVL. As you see, we are asked the current, V1, the voltage across this resistor, V2, the voltage across this resistor, and the V output, the voltage across these 2 components. So we apply KVL right here. Apply KVL. We have a source, 4.7 kilo ohm, a silicon diode, which consumes 0.7 volt in order to transmit a voltage. So the silicon diode is set in the forward bias direction. So we have a resistor and a battery. So E, as you see, E minus V1, because this is positive, negative. So this positive, negative, the anode side is also always positive, the cathode side is negative, positive, negative, negative, positive. So those of components which have the same polarities will be positive, and those which are different polarities like this, according to the direction of the current. So when we apply KVL, we set one of the component is positive and the other component is negative according to the direction of the current in their polarities. As you see, the current flows from this side to this side, this direction. So the current flows in clockwise direction. So it enters the negative terminal to the positive terminal in this component. So we say this such like component is positive. So you see this positive terminal to negative and positive terminal to negative. These two are the same. Also these three components negative. We set them because they consume voltage. They consume voltage. These are the sources. These two are the sources. These two delivers voltage. These three components consume voltage. So those of elements which deliver voltage, we set them positive, and those which consumes, we set them negative. So their summation will be 0. Their summation is 0. This is Kirchhoff's voltage law. So the summation of the voltage across the loop is 0, closed loop. So there is a ground right here. So the ground is connected. So V1 is this one and V2 is this one, 0.7 for the silicon to turn on the voltage, Vk, that means Vk1. So 5 volt plus, because of the polarity, these two have the same polarity in accordance with the current. So the current enters the negative terminal of both batteries, as you see, and leaves through the positive terminal. So check the polarities always when you solve problems. So applying KVL, so V1 means 4.7K times I. These elements have the same current because they are set in series. They are in series. So 4.7K times I minus 2.2K times I. 0.7 is subtracted from this element, which is equal to 4.3. So rearranging the terms, I is 2.07 milliampere. So once we calculated I, V1 means I times 4.7K. V1 is the voltage across this element. V2 is the voltage across the second resistor. So V1 is I times 4.7 kilo ohm, which is equal to 9.73 volt. V2 is the voltage across the second element, the second component, the second resistor, which is equal to I times R2. I is calculated, so I times 2.2 kilo ohm, which is equal to 4.5 volt. So in order to calculate I, now the final is to calculate the V output, the voltage across this one. So right here also we assume a closed path, like assume this is a multimeter. Assume this is a multimeter, this is a ground, assume this is a closed path. So we apply KVL to this loop, to this very loop, to this loop. This loop KVL. So we assume the current enters into this, leaves into negative terminal like this. We assume like this. So the current enters the positive terminal to the negative, and negative terminal to positive. So these two have different. So we will this is positive, the positive of the V output. The current enters the positive terminal of the V output, leaves into the negative terminal or the ground. So these two have the same polarities. The V output and the 5 volt is when we apply KVL. So when we apply KVL, these two have the same polarities because the current enters the positive terminal, the negative. But this resistor is assumed. We assume the current to apply KVL. So 5 volt minus I times, or we assume V2 minus V output, which is equal to 0. We know V2 plus because these two have the same polarity in accordance with the assumed current. So this is the odd from these two. So we know V2, we calculate V2 is 4.55. So we make 5 volt minus V2 is 4.55 plus V output is equal to 0. So the V output will be 0. We take V output to the other side, minus of V output is equal to 5 volt minus 4.55, which is equal to minus 0.45. V output is equal to minus. So this shows the polarity will be changed into this is negative and this is positive. So the V output is minus 4.55. That means the polarity is changed. The polarity must be changed. So this must be negative, this must be positive. This shows. So this is how we calculate. Thank you for your attention.